Something along those lines.
Low test, there we go. Okay,
Okay.
it's on. It was muted. Okay, so now we're recording. Thank you. All right, so somewhere I have my page. Here we go. Okay, so an insulated open feed water heater is used for steam power plant. So I have two inputs, one at T3, one at T5, and it comes out as saturated liquid at P6, but all the pressures are the same. So this is an open feed water heater, and I'm going to make that my system boundary. So there's heat transfer going on inside, there's all this mixing, but there's no Q across my boundary. There's no work across my boundary. It's steady state. So the first law, dE CV dt is 0 because it's steady state, equals Q dot minus W dot plus, and since we have more than one inlet, one exit, we're going to write summation M dot I times HI, then of course plus kinetic plus potential, but this problem doesn't seem to have any information about kinetic and potential, so we're going to assume it's 0. So I'm just going to put that one term minus summation M dot E, and then of course the enthalpy at the exit plus kinetic plus potential, but those we're going to assume the change in kinetic, change in potential is 0. So no heat transfer, no work. So I'm just left with the mass flow rate times the enthalpy at all the inlets is going to equal the mass flow rate times the enthalpy, the sum of those at all the exits, and there's only one exit. So this problem then becomes, we move this a little bit out of the way. So I'll move this to that side of the equation, and I'll get M dot 6 H6, which is my exit. That's this one here, my exit. Equals, and then the sum of all the inlets. So I have M dot 3 H3 plus M dot 5 H5. And determine the following. So let's see what we're asked for here. So I have M6, which is my exit. The pressure is 10 bar, and okay, I was told a little bit more. I guess I need to know the okay. So I don't know the flow rates here, right? So I'm going to have to, in this case, I'm going to have to solve for those two flow rates. So the enthalpy at the exit, the specific enthalpy at the feed water exit, I know that it exits as a saturated liquid, so the quality is 0. So I can find that enthalpy. So let's see if we can do that. I think I have my book right here. So maybe y'all can help me with this. So let's look up the properties. Oops. Bring that back. All right, so it's 10 bar and okay, so I have 10 bar and the quality. All right, so H6, all I know is that X equals 0 and that P equals 10 bar, right? So, but that's enough information. I go to the saturation tables, I look up saturated liquid at 10 bar, and I get HF is 762.81. Right, so HF at 10 bar. At P6. And that's equal to, so H6 is 762.81. So I've got this now. Plus I was told M6 is 65 kilograms per second, so I know M6. So now I know T3 and P3, so I can get H3 is a function of T3 and P3. I'm guessing that's probably superheated. T3 is 320 degrees C. So I go to the superheat tables, 10 bar, which is 320, and I get an enthalpy of 3093.9. Kilojoule per kilogram, right, from superheat table. And then H5, and it's a function of T5 and P5, and that is, didn't write down the other one, but T5 is 80 degrees. Well, 80 degrees is below the saturation temperature. The saturation temperature at 10 bar is 179.9. So I've got to go to the saturation tables of this saturated liquid vapor mixture. And 10 bar, and let's see, was I told anything else? So temperature, it's probably subcooled. Yeah, well, it is subcooled because it's below the saturation temperature. So this is subcooled. So I'm going to say it's about equal to HF at the given temperature at T5. Now, to be a little more accurate, I'd use the more exact calculation, but I'm going to start with this one. So I guess I could do plus, maybe I did it this way, VF at T5 times pressure, which is 10 bar, minus Psat at T5. So that's more exact. This first term is pretty good. If I need to be better, I do plus the specific volume at T5. So I use the saturated enthalpy at T5, which is 10 bar, so that is 762.81, which is the same as H6, right? I already found that one. 762.81 plus, and that's kilojoule per kilogram. VF, which is 1.1273. This is cubic meters per kilogram. And times the pressure. The pressure is 10 bar. If we do it in kPa, then that's going to be the units are going to work out so that I can add these units to they'll end up to be the factor between cubic meter per kilogram. kPa is the same as kilojoule per kilogram, so they're 1 to 1. If I can use other units, but then I'll have a factor in there. So this is 10 bar, which is 1,000 kPa, minus Psat, which is which is 10 bar. So that's Psat. So it is, let's see.
So you have to multiply by 100, so you can get the approximate.
So my pressure minus saturation pressure at this. So I am at. To think about this for a second. So I'm at the same pressure but a lower. Oh, I know what I'm doing. I'm doing the wrong temperature. So I was like, wait. So this, I'm doing it T5, but T5 is not 179. T5, so I was doing this is all at 179. I need to do it at T5, which is 80. So that's what I was doing wrong, sorry about that. I was using it at 10 bar. So at 80 degrees, which is a common mistake that students make, so I guess, but the saturation pressure then is 0.4739 bar, so 47.39.
Sir, what table do you go to the? Never mind.
Okay, and then at 80 degrees, it's 1.0291. And then I also need to write times 10 to the minus 3 cubic meters per kilogram. So 1.0291, and then this is 1,000 kPa minus 47.39, which makes sense now, because it was 1,000 minus 1,000, it didn't make sense. This is the saturation pressure at T5, which is 80 degrees C. And then this is the specific volume at T5 equals 80 degrees. And this should be the enthalpy, saturated liquid enthalpy at T5, which at 80 degrees, so this is table A2, is 334.91. So that's my H5. So now I've got H3, H5. Of course, so I've got cubic meter per kilogram times kPa, and you can work out the units, but that will it will be equivalent to kilojoules per kilogram. And then, so I get a number for that. Now I have all the H's. So now I have H3 and H5. And then one more equation I need, because I have two unknowns, right? M3 and M5. So one more equation is the mass continuity equation. But I think we can see that the mass continuity equation will give us that M6 has to equal M dot 3 plus M dot 5. Right? So, you know, the sum of the two mass flow rates coming in has to equal the sum of the mass flow rate out. And so, you know, this is M dot 6 was 65. This is one unknown. This is the second unknown. This is unknown 1, right? And this is unknown 2. So I've got two equations and two unknowns, and I just solve simple, you know, I solve M dot 3 equals 65 minus M dot 5, right? I put that in here, and now I have one equation and one unknown.
Yeah.
Solve for M5, and then after I solve for M5, put M5 in this equation and swap M5 in. Okay, and then just to reiterate, because I originally when I wrote this out, I was using the T5. Really, I was looking at the saturation rate 10 bar, but I do it as a function of temperature, not a function of pressure. So I should have gone to the 80 degrees. I wrote it right, and then I just doing it wrong. Looked up 80 degrees, looked at the saturated liquid enthalpy for 80 degrees, look up the specific volume at 80 degrees, the saturation pressure at 80 degrees, and then I end up getting that better approximation. It's not going to be too far off from this. Right? This isn't going to modify it a lot. I don't know if in the problem, if you just use that, would you be within the margin of error? You might be.
Okay.
But it's always better to add that and then decide later. Well, yeah, all right, I'm gonna stop this one.